Good afternoon. We will finish with a bit of physics, which is always my favourite way to finish today. So we'll start with question 1. So it says, which of these pairs of objects will attract each other? So which will try to move towards each other? So we've got a mixture of things here, haven't we? We've got some magnets. We know they're magnets because they've got north and south poles. And then we've got some metals. So what will cause us to have attraction? There's a couple of things that might cause attraction. All right. One is that we might have opposite poles. So opposites attract. You might have heard that saying before. So if it's a north and a south pole, they will attract each other. Or you might also have a magnet and a magnetic metal. So that will be the other option for attraction. So what are the magnetic metals? The most common one is iron. The other two are nickel and cobalt. Only those things will cause attraction. If it was a north and a north pole, repulsion. A south and a south pole, repulsion. So I'll give you just 10 seconds to have a quick look at these options, and it should be fairly obvious what the answer is. So clearly this is copper. That is not one of those metals. It's not A. B, we've got a south and a north pole. So it absolutely is B. We'll just double check. It's always worth double checking. North and a north pole, absolutely not. And this one, aluminium, is not a magnetic metal. All right, question 2. It says a bus takes 1.8 hours to travel 24 kilometers. What is the average speed of the bus? Now, it's asking for speed. You might remember the equation. If you don't remember the equation, you're very, very lucky this year. You have access to the equation sheet. So you can always, I would always encourage you to check anyway, as you have it, why not use it? So if you look down, this is to do with motion, which is in P2, which is forces and motion. And you see this is the equation that we need. Distance traveled is speed times time. We're asked for speed. Speed equals distance divided by time. Now, this is actually a relatively easy question, but I'm going to do it, 100% properly, so that if it's a bit harder, you'll know the way to lay it out and you'll spot the tricks that they might put in. So I would encourage you to draw a little grid like this. On the left-hand side are all of the things in the equation. So speed, and it's asked us to work out speed in kilometers per hour. Distance, which must mean it needs to be in kilometers. And time, which must be in hours. So we've been asked to work out speed. That gets a question mark. Distance, I can look at my information. I can see it's 24 kilometers. Does this match this? They absolutely do match. There's no tricks here, which is nice. It's a little bit easier than it could be. If this was in meters and it didn't match kilometers, then we might need to do a conversion. We might need to divide it by 1,000 to turn it into kilometers. And then time, 1.8 hours. And do these things match? They do match. There are no tricks here. Mr. Dekuma, did you have a calculator? So this then becomes really easy. Speed is my distance, 24, divided by my time, 1.8. Thank you. I'm demonstrating what you should never do in an exam. Never forget your calculator. All right. In every single exam, biology, chemistry, physics, bring it, use it. All right. You're allowed to, so why not use it? I used to bring a spare one to all of my exams, which most people mock me for. But the one time my battery ran out, I did not stand there panicking. I got my spare one out. It's very smug. Still had one at work. So 24 divided by 1.8. gives us our answer of 13.33. So it is recurring, but I'm just going to round it like this, which obviously is my answer B. So like I said, no tricks, quite easy. You might be thinking, why did I do it in so much detail? Because sometimes there will be tricks in there. It might be a little bit more complicated. Okay, question 3. It says, which voltage is the maximum voltage made when 4 1.5 cells are connected in series? Series means in a row. Okay, if you were watching a series on TV, you'd watch episode 1, episode 2, episode 3, you'd watch them all in a row. So what this means is we're going to get our first cell, we're going to connect it in a row with the second one, in a row with the third one, in a row with the fourth one, like this, all in the same direction. Each of them are 1.5 volts, and we have 4 of them. So you might immediately know the answer to this. But just for anyone that might not be sure, if you are an electron, all right, going on your day-to-day business, going around the circuit, you're going to pass through the first cell. You're going to pick up 1.5 volts of energy. You're going to go through the second one. You'll pick up another volt, 1.5 volts, and so on and so on. So we'll end up with 4 lots of 1.5 volts, which this is probably far too easy for every single person, but I'm going to check because I don't want to make a silly mistake. It is what I thought it was. It is 6 volts, which is D. Now, what they might have said, before we turn over, what they might have said, I'll do this in a little box. They might have said, what is the minimum voltage? So how could we work that one out? So they will sometimes ask this, maybe with just 2 cells, or maybe with more. Right, what you might do, and you might have done this in a remote control at home, for example, you might have put the batteries the wrong way round, like this. So you've got the 2 negatives touching instead of the negative going to the positive. And then you might have connected 2 more also in the opposite direction. So although you might think it's 1.5 plus 1.5 plus 1.5, actually, because they're the wrong way round, they cancel each other out. So this would be saying 1.5 minus 1.5 plus 1.5 minus 1.5, and actually the minimum would be 0. If you did them like this, it just wouldn't work at all. So why do we not do this in a circuit? Obviously it's pointless, it wouldn't work. All right, we're going to skip the next 2 questions because I want to make sure we get the 6 markers done. Now, the 6 marker, all right, very, very easy if you follow this method. All right, we're going to follow the methods, the ABC of 6 markers, and it makes it really, really easy. Firstly, we're going to do A, which is to annotate the question with anything that's useful. Highlight the instructions, maybe make a few notes to ourselves. We're then going to bullet point our answer. Right, the only requirement on 6 markers in terms of your writing is it makes sense. Bullet points are fine. And then finally, we're just going to check everything to make sure we've done everything we've been asked to do. So we've got 4 students running different races. We can see we've got distances, we've got times. I don't think there's anything particularly here I need to annotate, but let's look at the instruction. Use the information in the table. So maybe I'll just put a little arrow to it, just, you know, make it really obvious I need to use this. Sometimes you might have 3 or 4 different tables, in which case you need to use every single table. To describe, what does describe mean? Describe means say what you see. And compare. Compare means say what is the same, so the similarities, or what is different, so say what the differences are. So use the information to describe and compare the motion What do we mean by motion? And that could mean speed, it could mean acceleration, it could mean distance, and that is all going to be related to time. So potentially we need to do all four of these. So what can we say? Let's do the, oh no, there's one more bit, isn't there? We've got to make sure we do this properly. Use the data, use the numbers in your answer. So for me, what am I thinking? Right, describe and compare. Maybe I could start with that, but I actually reckon if we do some calculations first, use the data, that might make our comparisons easier. We might see a pattern, we might see a conclusion that we can write about. So what have we got? Distance, time. So can I work out the speed? Absolutely. Can I work out the acceleration? I actually don't think I can, because you need information about two different speeds, a speed changing. So this one I'm actually going to put a cross through, because I don't think we can do that here. Can I calculate the distance, or can I talk about it? Yes, we'll do that later. Same with time. So student A, the speed is the distance divided by the time. I'm not going to write this out in full every single time, because to be honest, I'll get a bit bored of writing it out 4 times, but I'm going to write it out once so the examiner knows I know how to calculate the speed. 50 meters divided by 6 seconds is 8.33 meters per second. It's actually 8.3 recurring, but I'm always going to round it to a number. I'm going to do this for B, C, and D quickly. So I'm going to say the speed for B is 100 divided by 15, which is 6.67 meters per second. C, the 100 divided by 14, which is 7.1 meters per second, and D, 200 divided by 31, which is 6.5 meters per second. So now I've got some information I can talk about. So now we can maybe describe what we see, or maybe we can compare. So what do I see? I see they're traveling at different speeds. I could say things, and I don't know what the mark scheme is. I haven't looked at the mark scheme and no one's given it to me, so I don't know. But I'm going to say the obvious things to start with. I'm going to say which student's the fastest. A is the fastest. I'm going to say which is the slowest. I'm going to say not B, C, no, D even is the slowest. It might get me marks, it might be too simple, I don't know, but it doesn't take me long to write it down. Are there any patterns? So we've got the slowest. In fact, to help me, I'm actually going to write it up here. So I'm going to go back, I'm just going to annotate it just to help me. 8.33, 6.67, 7.1, and 6.5. So what do I notice? They are traveling a further distance and the speed seems to be going down. Okay, it's not entirely true here. They travel the same distance, but it's kind of true. So it's worth saying it's a pattern. It's a difference between them. So I could say something like the further the students run, the slower they run. I'm going to take a second to think about it. Does that make sense? It does make sense. You've all run in PE. The longer you run for, the further run, the more tired you get. Probably the slower you get, unless you're really, really good at running. So that does make sense. So let's have a look at our question. Have we used the data? We've definitely done that. We've done some calculations. Have we talked about speed? Yes. Have we talked about distance? Well, actually we have, because we talked about the pattern. Have we talked about time? Maybe not. Maybe we can add a quick comment. Have we described what we see? We have done a bit of description, the really obvious stuff. Have we compared them? We've done a little bit of comparison. We did a little bit of comparison there. So we have done that. Have we done roughly 6 things? 1, 2, 3, 4, 5, 6, and the one on the page 7. A good indication maybe we've done roughly the right amount. The only thing we haven't done is time. What could we say about time? We could make a comment. There's a large range of times. We could say the longer they run, the slower they run. Either of those might be a good thing to say, just to be safe. It's certainly not going to hurt us. It's certainly not going to be wrong. All right, so we'll add that final thing in. The longer they run, the slower they run. So if I look at my answer, I've not actually written huge amounts. It's not an essay. I've not written, the next, Shakespeare play or anything. It's quite short. All right. But I'm pretty confident that will get me 5 or 6 marks because I've done everything it's asked me in the question. All right, let's move on to question 7. So we've got a book resting on a table. Draw a free-bodied force diagram to show the forces acting on the book. Use arrows to represent forces. This term here scares students a lot. Right? It scares some of my year 12s and 13s. All it means is a simple force diagram. And what do I mean by simple? All I care about is the main forces. So I'm not after 20, 30 forces. I'm after 2, 3, maybe 4 forces. That's all I need. Now they've given me a book. A book is really easy to draw. A book is this, or a book is this. If they'd said a cat is really easy to draw. This is a cat. This is a cat. Right? They're physics objects. All physics objects, whatever they are this or this. We're not going to waste time drawing the actual object. All right, so this is my physics object. Now, one force you always get for free, basically. This book is on Earth. Everyone knows there is a force holding us to Earth, keeping us in our seats. Everyone knows that weight is the force acting down. You'll notice I've used a ruler. It's always a good idea with diagrams and arrows to use a ruler. There's also a second reason I'm using a ruler. The second thing is this book is resting on a table. So it is still, it is not getting faster, it's not getting slower, it is not accelerating, which means the forces are balanced. It's not flying across the table doing anything crazy. Which means if my down arrow, if I've drawn it about 3 centimeters, the up arrow must also be 3 centimeters. So I need to draw an arrow that is roughly 3 centimeters up. Now I've actually been a little bit stupid here. I've probably drawn my arrows too long because it goes over the question. It's not necessarily a problem, right? The examiner will see that, but in the ideal world, we just have to move the whole thing down. And we need to label this force. So the book is on the table is physically pushing up on the book. So in this case, it is a contact force. Sometimes it's called a normal reaction force. The table reacting to the book, pushing it up. Right, let's look at one or two more. If this was a boat, I'll give you 10 seconds just to think to yourself, what arrows would I draw? What would I label my arrows on the boat? It's just resting on the sea. It's not accelerating. What would I label the arrows? So we always get one for free. It's weight, but the boat is resting on water. Water pushes up with the force of upthrust. All right, we'll do one more before we turn over. This time, the question is going to be slightly different. It's a boat, but it's accelerating. It's getting faster to the right. So I draw my physics boat. This time, you think, are there going to be two arrows? Are there going to be more arrows? Are there going to be any differences with the arrows? So we always get one for free. We get weight for free. I should have drawn that with a ruler. It is obviously floating. It's not sinking. So we're still going to have upthrust, but it's now accelerating to the right. So there must be a force causing it to accelerate. So that might be called the engine force, or it might be called thrust. And it's accelerating, so the forces this time are not balanced. The force trying to slow it down is going to be smaller than the force trying to speed it up. The force trying to slow it down, if you go running outside, running home after this, you'll obviously feel the force of air on your face trying to slow you down. So air resistance is probably the most common one. You might label it as drag. Drag would be fine as well. Okay, I'll turn over and do part B. So it says a teacher uses an air track for motion experiment. So an air track, if you've ever been to like an arcade or a cinema or something, you might have played air hockey, which is a game on a massive table, and there are holes in the table and air is blown through the table, which makes the little disc kind of float on a cushion of air. And when you hit that disc, it moves really quickly because there is very, very little friction. So it's basically like that, but instead of being a big table, it's just a long, thin track. So it only moves forwards and backwards. It won't move side to side. And it even tells us here, using the air track means that there is no friction between the glider and the air track. The teacher places the glider. So when you're talking about glider, not talking about something flying, it's basically it will be something that looks a bit like this. It will just be like a bit of card or a bit of metal that sits over the air track and glides on that cushion of air. So the teacher places the glider on the horizontal air track and gives it a small push to start it moving. Explain the motion of the glider. So I guess there's two things to say. There's what happens when the teacher pushes it, There's what happens after the teacher has pushed it. So when the teacher pushes it, right, that's fairly obvious. You know it's stationary, you know the teacher pushes it, you know it's going to get faster, it's going to accelerate. So it accelerates because, and we've talked about this already, because there is an unbalanced force acting on it. Now, after the teacher's pushed it, the teacher's no longer touching it. The air track is just moving on its own. So after the teacher has pushed it, there is no pushing force. There's no force from the teacher's hand. So what does it do? The glider moves with a constant, which means the same speed. The forces on it are now balanced. There is no friction. There is no push force. So it just continues doing what it was already doing. It continues moving at a constant speed, which some of you might remember is one of Newton's laws. It's Newton's first law. Right, we've got time to do a couple of short questions, so we'll just jump ahead to question 9 on electricity and do a couple of short ones here to finish. So it says a student uses the circuit in figure 17.2 to investigate the current in component X and the potential difference above it, across it. So current, potential difference. We don't know what this is at the moment. It could be a bulb, it could be a resistor, it could be something else. State the name of the measuring instrument the student uses to measure the currents. Everything okay, boys? So things in physics that measure things will be something meter, almost always something meter. If it's to measure currents, it will be, oh, that's far too many M's, an ammeter, not an amp meter. Some people do have a habit of writing this. That's not how you spell it. It's an ammeter. And then it says, draw the circuit symbol for the measuring instrument. This question comes up almost every single year. I would say 9 out of 10 years, this question will come up. An ammeter is measured or is put in series to measure the current. So it's put in a row. So we need to somewhere put it in the same loop as the component. You could put it on the left hand side, that would be fine. You could put it on the right hand side, that would also be fine. We've then got state the name of the measuring instrument that used to measure potential difference. Potential difference is a term, or the correct term, for voltage. I know we sometimes say voltage, we should say potential difference, and it's going to be something meter, and in this case it's a voltmeter. And voltmeters are always placed in parallel. So we make a new loop, a new branch to put a voltmeter in. So across the component, we need to make a new loop, a new branch, and put our voltmeter in. What we're actually doing is we're comparing the kind of energy of the charges before and after and seeing what the difference in their energy is. Well, I think I've finished there. So like Ms. Kuma said, she will put the answers to these on the Year 11 revision page, so you can finish them or go over them again at home. Well done for your focus and work this afternoon. I realise it is quite hot in here. Please put everything back inside your bag, and in a minute or so, we will start to dismiss you.